Hi guys, so in the previous video we discussed that covalent compounds can be classified into two types. There's simple molecular compounds and giant molecular compounds. Now we've already discussed this section, so if you're confused about polar and non-polar compounds and other properties of simple molecular compounds, you can go watch those videos. Now what we're going to be focusing on today mainly is going to be giant covalent lattice. So basically a giant covalent lattice consists of a 3D array of atoms, and these atoms can be of the same type. Like in diamond, the type that you have over there is just going to be carbon atoms joined together. Or it can be different types of atoms. Like for silicon dioxide, you have silicon and you have oxygen atoms. The next point over here states that these are going to be held together by strong covalent bonds. And the main thing over here is these bonds have to be strong and they have to be covalent. So these are 2 points that you need to remember. And the next thing that we're going to be talking about is going to be the different allotropes of carbon. And then we're also going to be discussing the structure of silicon dioxide in detail. So the next thing that we're going to be discussing is going to be the allotropes of carbon. But before we do that, we're going to define the term allotrope. So an allotrope is when two or more forms of the same element. So for carbon, in each allotrope, the main element that's going to be there is going to be carbon in the same physical state. So if one allotrope is going to be in gaseous state, the other one also has to be in gaseous state, but having a different atomic arrangement. So the element is going to be the same, the physical state is going to be the same, but the arrangement of the atoms is going to be different. And the first example that we're going to be talking about for allotropes of carbon is going to be graphite. So graphite basically consists of flat layers of carbon arranged hexagonally within each layer. And one carbon atom is going to be bonded to three others. So basically over here, if you look at this dot, all these dots over here that are made in white, I've highlighted them in green right now, these represent carbon atoms. And one of them is bonded to three others. So as you can see, this is one, and it's going to be bonded to three others. So this is 1, 2, 3. And since carbon has 4 valence electrons, because it's in group 4, one of these electrons is going to be free, it's going to be delocalized, and it's going to be available for pi bonding. So this is going to be the delocalized electrons, and these electrons are going to be free to move. And this is the reason why graphite can conduct electricity, and we're going to discuss that later on. The next point is that these sheets of hexagonal layer, so this is one layer over here, and this is the other layer over here. In the actual structure, there's going to be lots of layers, but I've only made 2 over here. And these layers are basically going to be stacked, and they're going to be connected by weak van der Waals forces of attraction. So the forces of the covalent bonds between each carbon atom, these are going to be strong. But the van der Waals forces between these layers, these are going to be weak. Now we're going to be discussing the properties of graphite. So the first one is that it has a high melting point and boiling point. And this is because of the fact that it has a giant covalent lattice. So a lot of energy is needed to break the strong covalent bonds that I talked about before. So between the carbon atoms, there's going to be strong covalent bonds. And for you to melt it or to boil graphite, you need to break those bonds. And for that, you need a lot of energy. And the next point is that it's a good conductor of electricity. So previously, I talked about how one atom of graphite is bonded to 3 other atoms. And because of that, since carbon is going to be in group 4, it has 4 valence electrons. And since 3 of them are going to be used in bonding, there's going to be 1 electron which is going to be delocalized and it's going to be mobile. So since it can move, it's going to be able to conduct electricity. The next point is that graphite is going to be insoluble in all solvents. It can be polar or non-polar, it doesn't matter. No matter what the solvent is, graphite is going to be insoluble. And this is because the solvent will not be able to penetrate the graphite lattice, and the main reason for this again is going to be the strong covalent bonds within the layers. So within the layers, within the hexagons, the covalent bonds are so strong that the solvent cannot penetrate, and because of that, it's going to be insoluble. The next point is that graphite is very slippery, and the reason for this is going to be the van der Waals forces between the layers. So now within the layers, within the hexagons, the covalent bonds are going to be very strong. But over here, these weak van der Waals forces that I discussed previously, these can easily be broken. So because of that, these two layers, if this is layer 1 and this is layer 2, these two layers can easily slide over each other. And because of this fact, because of the fact that graphite is very slippery, it's also used as a lubricant. So this is the reason. The next allotrope of carbon that we're going to be talking about is going to be diamond. So in diamond, the first thing that we're going to be discussing is going to be the arrangement of atoms in diamond. So diamond consists of a giant covalent lattice, just like graphite, and these carbon atoms are going to be held together by strong covalent bonds, just like in graphite. So over here, one circle, one white circle over here, I'm going to mark it in green. These green circles, these represent carbon atoms. And these are going to be held together by strong covalent bonds. So one atom is going to be tetrahedrally bonded to 4 other carbon atoms. So the arrangement in graphite was hexagonal, and in diamond is going to be tetrahedral. So one carbon atom is going to be bonded to 4 others. So it's going to be 1, 2, 3, 4, and this is the carbon atom I'm talking about. So what I've drawn over here, this is 1 unit of carbon, 1 unit of diamond, and these units are going to be joined together. So this is just 1 unit, it's not the entire structure. And electrons over here are going to be localized. This means that since one carbon is bonded to 4 other carbons, all 4 valence electrons are used in bonding. So there's going to be no delocalized electrons. And now we're going to discuss the properties. So the first property is that it has a high melting point, and this is because of the strong covalent bonds that are there between the carbon atoms. And these covalent bonds require a lot of energy to break. So that's why diamond has a high melting point. The second property is that it's a non-conductor of electricity, and this is because, like we discussed previously, it has no delocalized electrons, so there's no free moving electrons, and it also doesn't have any free moving ions. So for you to be able to conduct electricity, you need to have either electrons or you need to have ions that are free moving. And since diamond has neither of these, it is a non-conductor. And the next property that's there is that diamond is going to be very hard, and the reason for that is the same thing as for high melting point. The atoms are going to have lots of strong covalent bonds between them, and because of those strong covalent bonds, diamond is going to be hard.